Welcome to the video of our CVPR 2026 paper, OVI-MAP. Open Vocabulary Instance-Semantic Mapping. Online semantic and instance 3D mapping is essential for autonomous agents operating in complex daily environments, supporting downstream tasks like language condition navigation, manipulation, and facilitating queryable scene understanding for both AR and robotics. OVI-MAP is provided with streaming RGBD sequence with camera poses as input. And it incrementally updates a class-agnostic instance map and per-instance semantic feature aligned with the vision language models. For our motivations, most of the previous methods rely on closed-set, class-dependent semantic predictors or offline instance segmentation. But extending these designs to open-set recognition is non-trivial for several reasons. Some methods segment the instances first, then obtain their open-set semantics. However, object instance grouping becomes unstable and prone to fragmentation without semantic labels. And getting high-quality object proposals with post-refinement is too slow for real-time mapping. If we obtain a dense open-set semantic map first, aggregating the voxel-level open-set semantic features into 3D representations is noisy, without consistent 3D instances. It also leads to substantial computational and memory overhead to store these vectors. To address these limitations, our core contribution is an efficient, open-set semantic aggregation procedure that associates image regions with class-agnostic 3D instances and enables robust zero-shot semantic recognition. We reconstruct instances online in a class-agnostic manner, avoiding the dependence on closed-set semantic labels for object grouping. Then we introduce the object-centric view selection to efficiently aggregate VLM features, avoiding dense or redundant semantic fusion. Our approach first performs multi-view, class-agnostic instance segmentation, and incrementally lifts these instances into a global TSDF-based representation, producing a consistent 3D instance map across frames without requiring semantic labels. In Part A, we first fuse a set of class-agnostic entity proposals from the RGB images and the geometric segmentation from the depth image, in order to improve segmentation around contacts and clutter. In Part B, the refined 2D segments are lifted into a 3D point cloud. Each point is associated with a global 3D instance via spatial voting within the assigned voxel. It depends entirely on spatial consistency, not semantic similarity. Oversegmentation and multi-view fusion are handled by merging spatially close 3D instances. On top of the global 3D instance map, we introduce an object-centric view selection strategy that identifies informative viewpoints for semantic extraction. With the semantic embeddings extracted from the image's crops, we maintains a semantic feature vector for each 3D instance in the global map. In Part C, semantic features are queried from VLMs only when a frame's viewpoint provides non-redundant coverage of the 3D object surface. Semantic features are updated per instance using visibility-aware weighting. This method improves both efficiency and robustness while avoiding per-voxel storage of high-dimensional embeddings. In Part D, visual embeddings are extracted from two kinds of object crops: cropped image containing the object extent, and the masked version with their background pixels removed. We proposed a novel view selection strategy for this task. Usually, existing methods use the pixel counting strategy to select the views for semantic extraction of the instance. It prioritizes frames with larger object masking area, often leading to redundant front-facing views. The object-centric view coverage method maintains a spherical map of explored viewing directions and selects frames that provide novel perspectives of the object. Our object-centric view coverage method can yield a more diverse and informative set of viewpoints for semantic feature extraction of the instance. During evaluations, we use two datasets: 8 often used scenes from the replica dataset, and 18 scenes from the validation split of the ScanNet dataset. For the baselines, we split them into the instance segmentation task and the semantic segmentation task. For the instance segmentation, we achieve comparable or better accuracy to the offline approaches, while consistently outperforming prior online systems. To remind, Mask 3D was trained on the ScanNet dataset. The open vocabulary features of the instances are compared against the SIG-lip-encoded text embeddings of the label set defined by the datasets to find the most similar label. We evaluated the per-vertex semantic IOU and precision, and the per-instance semantic precision threshold at IOU score of the matched instances. We benchmark both our OVI-MAP and the baseline OVI-SLAM under a 30 FPS constraint, where only every in frame is processed to run in real time. We compare our incremental semantic aggregation using the proposed view coverage strategy against pixel counting and other baselines. Our method achieves comparable semantic accuracy while requiring significantly fewer VLM queries per instance, demonstrating efficient and scalable open vocabulary mapping during online exploration. To better understand how the objects are recognized, the heat maps of the instances in the scene are shown. It shows us how well the objects we query can be distinguished from the others. We calculate the cosine similarities between the semantic features of all instances and the semantic features of the query semantic label. Similarly, the instance highlighting from arbitrary text queries. Finally, we will show some ablation studies and the visualization of the semantic and instance maps